Hi, so this is a quick introduction to using the gamma spectrometer. This unit has the PMT, the 2-inch sodium iodide scintillator coupled to the PMT, and this is the HV electronics. From here you have the BNC connector here, which is labeled signal, which you're going to use to connect to the multi-channel analyzer. So this is a BNC cable, which means you twist it like this and then remove it. And the power supply, HV, etc. comes in through here. So this is an aviation type connector, which means you just hold this and pull, so do not twist, and put it back in. There is a notch here, so just be careful to align the notch and just push it back in. So once that notch is in place, you'll be able to just push it back in place. These two are connected to the multi-channel analyzer, which is completely USB powered. So here you have the USB port. You plug that in. This is an indicator LED. I haven't yet connected it to my laptop, it's just sitting there. So now let's look at the software. Now in the software, once you connect this, you can see that the little blue light has come on the hardware, and here you have, okay, select device, it's automatic. So now you have selected the device. This is where your spectrum is going to appear. So first we need to start. So go to the left side, instrument controls, click on start. The shortcut key is S on the keyboard. If you set a number here, it will stop automatically. If you don't, then leave it at 0. It will just keep acquiring. The threshold is the noise threshold, the minimum channels that you want to reject from the bottom end. So let's remove 20 channels only. It's pretty low noise, so 20 channels. Start acquiring. Now this is a list mode 2000 channel MCA. Okay, it's a 2K MCA. So every event is dumped across to the computer, where it is sorted into a histogram. So if you want the individual list data, you should set a list save file, which you don't really need. It's just time versus event, time, event, so on. It's a huge column. Then you have to sort it in bins. Since it's a single parameter device, you're not looking at any coincidences or anything. So list is just, you just use this direct histogram view. If you want to save the histogram, you have this button at the bottom. You can add your comments here, whatever this is. There is the contents that are being saved. Left side is channel number and the right is the counts at each channel. And you can just save this as a CSV file. Okay, so we have about 50 seconds of data now. I'm just going to stop this, pause the acquisition. I can actually resume it by clicking start and say, do not clear the old spectrum. Just uncheck this box and let it proceed. So this is background data basically for 54 seconds. So I can save this background, save acquired CSV as background, and save data. I'm going to place this inside here and call it TMP. So it will add the tmp.csv extension, and background has been saved. Now let's acquire fresh data using a cesium source. So I'm going to place cesium in front of this here, and just click on start here. Okay, so now what you see is you have a nice sharp peak, which is at 662 keV. Currently this is not calibrated. You have to calibrate with some standard source. So let it acquire for some time. Okay, so for calibration, you have the calibration menu here, but the easier process is first you add a region using this plus symbol here on the left side, or press the R key. Now you take this region, drag it, center it around the peak that you want to use as your calibration fitting, reference, and say fit, or press the F key. So this will give you your calibration menu, where it has already fitted your one reference point. So you have 30 keV of 30 channels of FWHM, 7% spread. So this is the channel. It's automatically filled in the centroid here. Here you have to enter the actual energy in keV units. So 662, 661.7. Now apply calibration. So when you do that, it says, okay, this is the polynomial slope plus, there's no offset obviously because we have done single point calibration 0 0 and this point. So it has calibrated, and now if you click on the graph and just say fit again, this time the centroid here is shown, whatever, 661.93, and the channel is shown in brackets here. Okay, so that's how you calibrate the device with the standard source. Or you just you note down this channel versus energy, and you can later on just go to the calibration menu and just feed those in to calibrate. The normal process for instruments is that you calibrate it every time you use it, because there are temperature coefficients that will come into play. For example, your sodium iodide scintillator has an efficiency that changes by about 0.3% for every degree in temperature change. So this is going to affect your readings, right? So you calibrate it at whatever temperature you're using it in. Now, one other thing, yeah. So we've calibrated. Now the next step is baseline correction. Okay, so baseline subtraction. Let this go away. So click on the baseline menu here, and there's a red line that has appeared. So here you can adjust the smoothness parameter, you can adjust the peak selectivity, okay, and see the optimum thing for subtracting your baseline, and this is iterations. Now when you click on subtract, it has removed as per this red line whatever is below the red line. Now you can play around with the thing while it is subtracted to get the optimum appearance that you want. And okay, so that's baseline subtraction. Now for your applications, you have huge number of isotopes. Okay, it's background basically that you're studying in health sciences, so it's going to be one big exponential decay sort of thing that it looks like. So you're going to need the log view. So this is the next to the baseline button, you have log view. So this is the log plot, and in the log plot you can see your cesiums here, the other peaks are here. There is something at 2.4 MeV and 2.6 closer to right. So that's your log view. You can also use summation, which is the number of events in a particular region. So it says 66,000 events have occurred within this little green region. You can add multiple regions for 2-point calibration, etc. So you can center it around another peak of which you know the value, and then say fit, and then these two have appeared. So now you have like these two, and then you can use that for calibration. Okay, now to save this data, just click on save histogram, add your comments and save data. It will save it as CSV. Saved plots is a tab here. You can either directly open a histogram, or you can select a directory. For example, the MCA that you have, there is some test data. So this is different test data. Let me just stop acquisition so I can view the I'm just going to stop this and clear this in the hardware also. Yeah, saved plots. So here you have your 3-hour spectrum. So there is cesium, cobalt. So this is at a higher voltage, which is why it's shifted more. But let me look at this here. Yeah. So this is cesium, and there is cobalt 11731332, and there is also americium. I put in americium 241, which has a 60 keV peak. So your saved data will be here, and in the bottom menu you can change things like threshold and okay. So I think that covers a basic introduction on how to use this device. Background subtraction is here, but for that you're going to need to get fresh data. Okay. So the background was for about 50 seconds, which we took in the beginning. So let's wait 50 seconds. And after that, I'll just say subtract background and load that particular file. So background can be any CSV file. So it will load, and of course negative values will be clipped off. And it shows the counts here. So if you click that, it will show you the count rate, instantaneous as well as the average value. So about 970 counts you're getting per second. And just stop this. Okay, so this is your graph here, right? So you have this shape here. This maxes out at about how much is that? Index 138 is about 163 counts. So now if I say subtract the background and data, it's called TMP. So you see this portion has suddenly taken a dip, right? So that's all background, low end noise. Yeah. So thank you. I hope I haven't left out things.